want to talk to you in a little bit more detail about a few topics we've talked about recently. So the first one is model selection. And in this data set, it comes from ISLR2. It's a data set on salaries in baseball. So for these individuals, and we omit the individual name because if we included the variable of individual name, we'd be able to exactly model and specify there's a one-to-one relationship of the variable salary to the individual. So that wouldn't be a good thing to do. But we have statistics. So for example, if we want to make a predictive model for how much we should pay someone, we have the number of at-bats they have in baseball. We have the number of hits, the number of home runs, RBIs, walks. So RBIs is a number in baseball called runs batted in. Walks, which is another technical term. How many years they've been playing, the career at-bats, career hits, etc. What league and what division they are in, a term called putouts, assist, errors, and then finally we want to model the variable called salary. Okay. So there's a lot of other analysis we could do, but I mainly want to focus in on subset selection and model selection. So I'm going to ignore the fact that you may want to transform this data, but most likely you'll find that a transformation could be useful. Okay. Instead, I'm just going to focus on the different methods. So if we do a backwards model selection, we use the reg subsets in the LEAPS library. We specify backwards, and then we're given this input. One thing I want to notice is that once this variable career runs is in the model, it's always in the model, and that's denoted by, we can see that because there's always an asterisk below the variable. Okay. Likewise with hits, it's the second variable or second most in this procedure, and once it's in the model, it's always in the model. And we see that with all these variables. That's a feature of backward model selection. Okay. So we have the best one variable model, two variable model, three variable models, all the way up to 19 variables. So we might want to know what's the right model. Is it 2 variables? Is it 10 variables? What is it? So we're going to use a metric, and we're going to use the Bayesian information criteria to compare models. So we'll make a plot of it, and the model is indicated on the x-axis by how many variables it has. Then on the y-axis is the Bayesian information criteria. So the general rule of thumb is the lower the BIC value, the better. So if we were to take the minimum here, that would lead to this model right here. Okay, and we'll return to that model. Okay, so it looks like we'd have it looks like we'd have 8 variables, and yeah, it tells us 8 right there. We'd have 8 variables under this procedure using the criteria BIC. We might very well get a different model if we'd used a different criteria. In fact, that's extremely likely. Okay. But now let's suppose we want to use best subsets. So if we use best subsets, this is the output we'd have. And notice when we use backward selection, so for instance, once the variable was in backward selection, it was always in. That's not the case here with best subsets. So here this variable happened to be one of the best 7 variable models, but then it wasn't the best variable to be included for 8, 9, 10, etc., all the way up until 15. When we hit 15, it says, okay, you should go back in the model, you're best for it. So once we're statistically significant, we're not always, it doesn't guarantee that we're always in the model subsequently. Okay, so keep that in mind, that the best subset, that's one of the unique features of it and distinctive features of it, is that the variable does not always have to be in it subsequently. Okay. So if we run this procedure, we're going to have our best 2-variable model right here. We're going to have our best 16-variable model right here. And so this tells us what variable should be in the 16. So the question is, which model, 1 through 19, a model with 1 through 19 variables, which one should it be that we use? Well, if we run this, we could plot it, also using the Bayesian information criteria, and we'd get a 6-variable model with best subsets. And this would be our model that we could look at. Okay, and notice these two models are different. With best subsets, we chose 6 variables for the minimum. With backward selection, we chose 8. So the two methods produce different models, even with the same criteria, the same metric. Okay, so the model that's produced by best subsets is this model right here. These are the 6 variables, and I reprinted it out not only to get the estimates, but mainly to look at the p-values. So here it happened that the p-values were all significant. That's great, but that's not always the case. So just know that when you run these models, you need to investigate the models a little bit closer to make sure they're statistically significant, and or to tweak the models a little bit, especially if, for example, you want to consider perhaps interactions of a few variables. Okay, so this was the best subset model. If I use the best subset model, we get an 8-variable model, and notice these are all the variables here, and they are also all statistically significant. Okay, so it looks like we would have, if we'd gone with the best subsets, we would have selected 6 variables, and this model indicates that there were additional variables that do affect the output. So it indicates that perhaps one model might be more appropriate than the other, and perhaps you could use an ANOVA F test to compare the two. And in fact, you can. I'm not going to do that, but just note that you can, and you always want to check for statistical significance. If you ever get a model without statistically significant variables, you need to remove that model. So for that variable. So for example, if you run backwards model selection and then you check to see what the model looks like, and you look at the statistical significance of the variables, if the variable isn't statistically significant, you want to then remove that variable. It's not a good statistical practice to have variables in your model that aren't statistically significant. So the p-value is really important here. Okay, to know that you have a model in which all the variables affect the output. Okay, so that's just a few things to note. One other thing we talked about was something called leverage. This is the formula for leverage. And points with high leverage are points or observations that can affect the regression line ability to estimate the coefficients, and can leverage the regression line away from the true estimate. So it can play a significant role in the model's ability to estimate the variable, estimate the coefficients. Okay, and it doesn't mean that it's estimating it wrong. It just means that it has a lot of influence. So a couple of things to take away here. Leverage is a measure of how far the observation is from the average x value. So the further away we are from the average x value, the more leverage we have, okay? And notice this is entirely in x, not in y. Every single point has a leverage of at least 1 over the number of points, 1 over n, okay? Okay, so leverage doesn't mean that the point should not be used in your analysis. It just means that it could influence your results significantly. Another formulation is Cook's distance. Okay, now Cook's distance, this takes into account how far the predicted value is from the actual observation, and it's not clear. It's not clear that it also, it also is a measure of leverage, but you work through a lot of ugly formulas. You can massage this equation to also involve leverage. Okay, so Cook's distance is a measure of kind of its squared residual, or how much of an outlier it is, because it takes into account the predicted value or the residual or the error of the observation, and also how influential the point is. That is its leverage. And then, like it says, there would be a lot of identities you want to prove it, but you're just going to have to take my word on it. Okay. The residual, which is what's in the numerator, that's the indicator of the outlierness. Okay. Points with large Cook's distance can affect normality, regression estimates, and your p-values. So you want to be really careful with things with Cook's distance. Okay, so in this function below is going to generate an equation that belongs to the true regression equation is 2x plus 1. I'm going to generate points according to this line. And then I'm going to output some things. So here's the scatter plot. Only this last point here is the one that I'm putting into the data set. So all these other points, so by the way, these points, their size of the point, how big they are, is related to their Cook's distance. So points with bigger Cook's distance are bigger. So we can see that by points that fall off of the regression line, like this one. But the only true point that I'm doing here is this one right here, that very last observation at 1 and 1, 3. And we can see that right here. Okay. So there are all these other points, and they just randomly have large Cook's distance due to the random error. This is the only one that I'm inserting manually or artificially. Okay. Now we can see that it has a larger Cook's distance. These are the hat values, which is a measure of how far they are from the predicted value. So none of them are too bad except for that last one. Then here's the plot of the Cook's distance. So even though it has a large error, it's not actually that unusual and doesn't have that much leverage. Okay. Now let's look at this next example. So as you can see, the point with the most Cook's distance is this one right here, that one on the far right. And then the other points, they're not too close to the line, but they're not actually going to be that influential. This line at the end is going to be what can pull it. Okay. And we can see that the regression line, it was able to estimate as 1.85, and the intercept's 1, and it correctly noted that x affects y. And this is accurate because, for example, in the function, the true equation is 2x plus 1. So that 1 point didn't have too much of an effect, okay? And we can see that that 1 point has a lot of, if you will, leverage and is an outlier. So with this Cook's distance measure right here. And in terms of this residual versus fitted, it doesn't look that bad, okay? Okay, now let's look at the last example here. So here's the last example. We can see all these points have a very small Cook's distance. The one that really affects it is this point at the end here, and we can see that now that point, it is really affecting its ability to estimate the value of x. Instead of 2x plus 1, it estimates 3.55x. So the estimate is quite off, and the intercept is also off, but not as bad as the slope, okay? We can see that it really has a large Cook's distance, not only from this graph, and we can see it's an outlier with this hat value being so far compared to the others. It's affecting the equal variance here. And then we can see its Cook's distance value here is just off the charts compared to all of the other points, okay? So Cook's distance, it's kind of a measure of how influential it is and how much of an outlier the point is. And so it kind of suggests if you should remove a point. But this is just extra information with this Cook's distance and this leverage. Don't dive too much into that or even at all for your final project. Okay, thank you very much.